Okay, cool. I think we're all ready, yeah? So the Linux people in here, I guess, know what I know what I'm going through, trying to get presentation set up. But anyways, thanks for your patience and thanks for having me. So I'm Griffin. As Tom mentioned, I'm a client of your guys with a couple of projects which I'm working on. So I'm like a data scientist, statistician. It's my background, with some software engineering thrown in there. And I have been building Prism for the last little, we launched at the beginning of 2024 with my partner Guy, who's in the back. Thanks for coming. And yeah, so I have been working at ETH the last 5 years, just shortly about me, as a data scientist, and then recently got into starting some ventures, and have been developing software for these ventures. One of them being Prism. We are building search software in AI. So it's actually kind of perfect that we had a talk from Kevin on search, and now I will be like AI powered search, and then next is just pure AI. So it's kind of a perfectly designed evening, I would say, actually. So what do we do? Really, like in essence, so Prism is a software that's designed to index your knowledge, and then make it searchable, right? So this is, I guess you've heard of a lot of tools in the very recent months which are doing similar things, right? So AI, the developments in large language models have more or less empowered us to build a new level of search. So there's a new search paradigm that allows people to find information that they need when they need it better than they could before. So what makes Prism special? We support local and custom deployments of these searchable AI systems. We have a high bandwidth interface for indexing your knowledge. So this means through the user interface, you can scrape like 15 sites at a time, I think it's limited to. But if you sign up with an API key, then you can just index thousands. Just do it to your heart's content, you know, I'm sure there's some system engineers in here who would love to test the limits. So I welcome that. And then we are in the near future aiming to support the synchronization of knowledge sources. So interesting thing about knowledge, it's changing over time, right? So knowledge is always being adapted, being added to, improving, and so should your knowledge base, right? So the knowledge you're indexing in the back end should reflect these changes that are happening in life. So I don't think I need to sell search to IT people, right? But just like I had to include this slide, right? How much time is spent searching for existing information by employees each day? So there's a survey I'll show you. It said 3.6 hours or whatever. But for IT people, I think it's even more than half of our day is spent looking through documentation, trying to, at least depending on what you do exactly. But there's a lot of information that we have to manage. You know, building abstract software systems. There's many different dependencies, and all of them are interacting, and you have to understand them, keeping them in working memory, right? So, but the main reason, at least in the survey, people answered the information is stored across multiple locations, right? So how do we solve that? We index everything into a central repository that can be searched over. And that's what we're aiming to do, so that we aim to empower anyone to be able to build a searchable database with a few clicks or a few lines of Python or JavaScript. So let me back up and just quickly talk about like the evolution of search. So I probably don't need to explain what this is. Probably we all remember looking through the little cards to find the author's name on the book, or the book title, to go look through the library to find, you know, where you can find the information you need. But that was like one of the first search algorithms, right? Is this card catalog. But actually the first like computerized search algorithms was is built on Boolean retrieval, and this is really straightforward. So you just have your Boolean logic gates, right? Ors, ands, XORs, nots, and you can construct some kind of query phrase which should be submitted to a database, and then you can retrieve information this way, right? So here, yeah, you see how it works, and I think everyone's familiar with this, right? You can just write a simple MySQL query which does the same thing. But the next stage in the 70s, like the next like level of search, automated computerized search, is the inverted index and frequency tables, which are a really similar idea, but here I'll just show a frequency table. So the idea is pretty straightforward, right? You just count the number of named entities which appear in a given document, and then you do this for every single one of your documents, which are each rows in a data table. And then rather than having like just a true or a false condition on your queries, you now have some notion of like distance or similarity. So between the user's query and the documents which you're searching over. And this is kind of cool because this is more customizable, right? And I couldn't give a presentation on information retrieval without bringing up Larry and Sergey, right? So PageRank, just to self-search one more time, like the extent to which this algorithm changed the world's economy and all of commerce is kind of impossible to overstate, right? So this is a incredibly important development in the last like 30 years that these guys built. Many other people were also working on this, right? But this algorithm relied heavily on keyword matching in the beginning. So these like keyword tables, which I showed, then synonym matching, and ultimately context matching before it evolved into actually an entirely different algorithm, which was later adopted into Google's paradigm. Guy can tell you more probably about what Google's been working on. So he was working there for quite a while. But what we really want, right, is semantic similarity search, right? We don't want to just search for keywords. I don't want to have to search. I don't want to have to even know the words that I'm searching for in order to find them, right? If I want all books by Douglas Hofstadter, I should be able to get Gödel, Escher, Buck, and I Am a Strange Loop immediately returned to me by just typing the guy's name in. So, but this is more difficult, right? Because now you have to introduce some sort of measure of similarity between individual words, right? So you could imagine the way like a first approach at this might be to sort of construct some probability that two words appear in the same sentence together, or the probability that two words are adjacent together in the same sentence, or the probability that two words are on the same website. So you can estimate these probabilities and then ultimately construct an adjacency matrix, which of course is one on the diagonal because every word is completely similar to itself. But then you have more or less some measure of probabilistic measure of similarity between two words, and this extends to multiple dimensions, right? So you can do this for 3, 4, 5 words, 6 words, and this is where AI comes into the game, because actually AI or machine learning, all these modern tools, the problem that they solve is to estimate probability distributions, right? So if you can transform a problem, any problem, into a problem about probability distributions, then you can construct some AI system which can solve this problem. And because now, with the advent of semantic similarity search, multidimensional similarity search, we've transformed this problem of word similarity into a probability distribution, which can then be solved more or less by AI, right? And when I talk about probabilities, like you can think about it like, what's the probability that it rains tomorrow, or the probability that the next pixel in this sequence is blue, or the probability that the next word in the sentence is cat, things like this. So the trick is to transform a problem into a problem about probability distributions, and then you can make AI solve it. So I won't go too into details about the specific models. So that's the next talk. But just for now, I will tell you there is a black box which you can put words into, and out from this black box comes a vector of floats, or a vector of real numbers, right? So and these real numbers are essentially, this black box is designed in such a way that this vector of real numbers is more or less characterizing the semantic meaning of the words which the user put in. So there is some way of mapping English text or any language text onto some vector of numbers which represents the semantic meaning of a word or phrase. And this is, I will translate between vectors and points in high dimensional space during this talk. So just, so we're on the same page, like a 2-dimensional vector or a 2-element vector is a point in 2 dimensions, 3-element in 3 dimensions. And in this case, we're using like 4,000 element vectors. So this maps to a point in 4,000 dimensional space, more or less, right? So this is like an easier way to think about it moving forward. So what does Prism do? How does Prism leverage this technology? So we take a user's query and we plug it into this black box, which turns the query into an embedding or a vector of floating points or a point in this 4,000 dimensional space. And then you can just compute the Euclidean distance or the cosine distance. You have some, very simple functions you can use to compare this vector to all the vectors which are already existing in your database, right? So you can think about this as like looking for the nearest neighbor. So this is fundamentally a nearest neighbors problem, where you have some set of points floating around in this 4,000 dimensional space, and the user submits a point which goes there, and you're searching for the neighbors around this. And this turns out to be actually kind of a hard problem to solve. There's a lot of work, which many PhD theses have been done on this exact problem. And so implementing a scalable solution for this is not actually trivial, but I'll get to that in a minute. So we have the similarity search. So once you've established which vectors, like how many vectors you want to extract and which ones are most similar, then you just have your text now, right? Which you initially index. So the user initially indexed all of this text, and you have your phrases here, which were in your database. And then what you can do is you can kind of smash all of this context together into a prompt, which you then feed ultimately to a large language model, which is able to respond to the user in an intelligent way, right? So the user asked you if Larry Page and Bach were strange loops, then was Escher related to girl? Some nonsense. And then you tell the LLM, okay, here's some additional context, and then you provide it with the context which you initially extracted during your similarity search. And the LLM is able to give you a contextualized, like coherent response about the stuff that the user asked. And just to zoom out so you can maybe kind of see it a bit better. So the user makes a query, the query is embedded, there's similarity search, and then the database, you get your text, which is then fed to a large language model, which is then responding to the user. So this is kind of a cool way to retrieve and then reorganize information in like a digestible way for users, right? So there's further considerations actually. So like, yeah, there's some limits on this system, but there's quite a lot of improvements that you can make, right? So one further consideration is you can search over multiple indices. So we can do our semantic similarity search, excuse me, combined with like a Lucene index search, like Kevin has done in his search engine, right? So you can actually combine the results of both of these similarity searches and provide that to a large language model. And you can also provide metadata from the user's query, like, okay, this user is an employee, or this user is not an employee, or this user is in Switzerland, or this user is in America. This is similar to like what the algorithm RankBrain does, released in 2015 by Google for contextualizing user queries. And indeed, so Microsoft Azure, they're like working hard on this information retrieval problem, and they found that this form of like hybrid indexing is the best out of any of the different indexing methodologies. So you have like here is keyword search, and basically, they give here on the y-axis some quality of retrieval. This is actually a really difficult thing to quantify, so it's warrants further discussion. But basically, you have keyword search, vector search, and then hybrid search here. And then they also introduce some semantic ranker, which this paper was in, I think, 2022. I don't think the ranker is necessary anymore because we have much larger models now than we did even in 2 years ago. But in any case, this like hybrid indexing methodology works really well for retrieval of information. Now, a quick word on nearest neighbor, because I know a lot of you are probably like the system engineers in here are wondering about how the limits of this system, right? Because this is a lot of overhead. This is a lot of infrastructure to maintain and everything. And one thing you can do is like a KD tree index, which stands for K-dimensional tree index. And this speeds up the nearest neighbor search by ultimately here's a two-dimensional case, but you can imagine in 4,000 dimensions that you partition this highly dimensional space into different sections. And then when the user submits a query, you kind of just go along this tree. Is it to the left or right of this partition number one? Boom. boom, and you kind of just do this repeatedly. So, you know, we have a tree which partitions our space, and we are able to, you know, we ultimately end up in a bin somewhere, one of these leaves at the bottom of the tree. And this is like a fast way of finding your point. Now, if you're observant, you will notice that actually it's not guaranteed that you're going to find your nearest neighbor by doing that, right? Because I might end up in this bin partitioned by 5 and 9, but I end up right here, very close to this guy, right? So you have to backtrack up the tree after you've arrived in one of your leaves, and you know you know how far you have to backtrack by calculating the maximum distance between the point that the user submitted and the furthest point in your partition. And then you construct a 4,000 dimensional hypersphere. I'm sorry, I had to say that word in this presentation because it's so fun. And then you know, backtrack up to that distance and then back down and search all of those leaves. This is a way that you can speed things up. The problem is these large trees suffer from the curse of dimensionality, right? Because we would like to make these vectors as long as possible in order to characterize as much semantic meaning into a single vector as possible. Now, as these vectors expand, the dimensions expand, these trees grow really tall. So you imagine the number of partitions you need in order to index one of these tables is massive. So actually, this kind of breaks down at some point. It takes longer to search over the index than it does to just brute force your way through the whole data table. So a better way is approximate nearest neighbor. And it turns out you can save like you can save an order of magnitude of time by accepting the approximate nearest neighbors rather than the exact nearest neighbors. And for this, we use FACE. So this Facebook AI similarity search library from Meta. And then we're using embeddings from this French company, Mistral AI, who's producing the coolest language model. They're one of the coolest companies in the space right now, I would say, because we've stepped into some parallel universe where the French are the most innovative in Europe, and Meta is releasing open source technology, and OpenAI is closed. So somehow that's where we find ourselves. And yeah, this is I just go over this quickly. This is a cool algorithm. So basically, this space algorithm, the way it works is it also partitions the space. So this is also in 2 dimensions, but you can imagine it in more, into these regions called Voronoi cells. And then you just compute the distance between the user query and the center of each of these cells. So then you know, okay, which region my nearest neighbors are in. And you can go, okay, my user query is here, but I'm in this region. And then you just search over the points in this region. And this allows you to do some really, you know, massive reductions of your search space, right? But again, you're not guaranteed to find the nearest neighbor. So you do these reprobes. So you can do 1, 2, or 3 reprobes. So let's say you end up here. You have you can probe 1 or 2 or 3 or 4 or 5 times to check if you have closer neighbors in those regions. But this has a huge effect on speed, right? But the really cool thing about this algorithm is you can dynamically choose basically how many probes you want to make into these neighboring regions based on, let's say, your time budget and how many rows are in this data table already. So like if you have a database with 1 million rows, but your time budget is like 1 second, then okay, of course you're talking about like using 1 or 2 probes here, right? But if you have, let's say your time budget is a little higher and you have maybe a bit fewer vectors in this data table, then you can use more probes and get more and more accurate information. So there's some way to sort of like scale this thing dynamically as the amount of information that you're indexing increases. Now there's a way, so talking about improving future results, one really cool area of research that's super hot right now, I would say, is like teaching neural networks to index. So like using a neural net actually as an index for a database. So rather than searching over all of these regions for the nearest neighbors, you're actually just asking a neural net to provide you its guess. So it guesses, you basically train this neural network to guess what is the closest, you know, set of points in this region. And that's also a form of approximate nearest neighbor search, which works in some research papers, it turns out. And then searching over knowledge graphs is a really cool thing for the keyword retrieval. So for the keyword side of things, right, you can construct knowledge graphs in like Neo4j, or Google has their giant like world knowledge graph or whatever. But a knowledge graph is kind of simple. It's just made up of entries in a table like object, relationship, object. And you can visualize this in a graph like, okay, yeah, Barcelona is a country in Spain, and you have this set of objects with their relationships. And when a user makes a query and you stumble upon a keyword, which is in this knowledge graph, you can decide sort of like how many steps away from that object you want to go in your keyword search for indexing information to return to the user. So this is maybe like way into the weeds about how to search for information, but there, just to show you, it's not a super straightforward, trivial problem to solve, right? So search seems, it kind of can seem that way, right? Because Google has existed for most of our lives, and Google is awesome. Well, the company not, but their search algorithm is truly awesome. So yeah, I will show you briefly, like super brief, because I'm sure that I'm almost close to my time, but like this is so we're still working on this software, right? We're in like very early stages of development, but we have integrated a few different models here. And then you can add your knowledge bases dynamically. Let's say there's a new version of Next.js or something, Next.docs, and you want to index this information so that your language model knows about it, because they don't maybe necessarily automatically know about it. So I can, like, let's just say go to the, I don't know, just a docs page. And like I said, through the front end, you can hit about 15 websites right now. But if you get an API key here, you can do as many as you want in the back end. So now we've already scraped like 15 links from this site. And what's happening is our bot is reading all of the text information, which is on these websites, and will start hopefully indexing it live. So as Kevin mentioned, building these indexes is not the fastest thing in the world. We've tried to make it like more or less quick enough to be acceptable by retail users, right? So that this is more or less usable. And then, yeah, you can take a model of choice. My favorite is actually Mr. Large, and you can say, let's use him. He's a bit smarter, yeah. Okay. Tell me a bit about app routing in Next, and then hopefully this thing, there's always the curse of live demos, right? But okay, so he's able to read the information. This index is reinstantiated every single time a new document comes in. These aren't actually new documents that are flashing down at the bottom here, but yeah, and then, as I said, the curse of live demos, right? So this is what can happen sometimes.
You can select the previous conversation.
Oh, thanks, Guy. Yeah. So you have conversations to manage. Yeah, you can manage knowledge in this way. And we're still adding, we have a lot of features to add to this software still, but you can test its limits. This is a test key. You can create API keys, boom, like this. And then we have a JavaScript wrapper and a Python wrapper, and you can drop this into Python, and in 3 lines of code, you have uploaded, potentially your entire computer worth of information if you want, and can chat with these documents. So this is something potentially interesting. And yeah, the benefits, we have full service API, just a short little pitch since I talked a lot about tech stuff, and then access to the best language models in the world, gigabytes of storage on our platform, unlimited retrieval, and built-in high-level web scraper for adding knowledge. And then soon to come will be like these, fully private enterprise solution, more mobile responsiveness. So please don't try this on your cell phone. Just go home and use it on a desktop because, yeah, anyways. Integration with Google Drive, Microsoft, OneDrive, Slack, Teams, all of the softwares that people use. We would like to be able to provide a simple interface for people to index their knowledge on these platforms. Organizational controls, synchronization to knowledge sources, and Am I missing stuff from our like short to medium term roadmap?
No, I think that's the gist of it.
Okay, I characterized it. Good. And I made a code for you guys. If you want free stuff, either come and talk to me or just use this code when you check out. You can have, yeah, just message me on LinkedIn, guys. I'll give you as many credits as you want, right? So just come. Yeah. There's no limit for the people at 9, right? So anyways, we need this face library I'm using for indexing in the back is a GPU, also a GPU library. And I heard that someone has some GPUs around here that could maybe be used in the future. So anyways, guys, thanks so much for your time. And that's all I have. So. Oh, yeah. And do we have time for questions? Or...
Yeah, 3 questions.
Yeah.
I have a comment. Actually, Solar can generate a knowledge graph from
Oh, really?
Data and index. Yeah. I mean, you have to like engineer a little bit, but if you're interested, I can.
Yeah, please share that with me. That's very cool. Yeah, very cool.
So, what's the kind of optimal index size that you need to build to get the best results out?
Yeah, this is a great question. Actually, this is entirely dependent on domain. It's entirely dependent on the type of text you're indexing, the language of text. Actually, this is a really tough question to answer, but I will tell you that it will be partially answered in the medium-term future by, let's say, AI agents who are going to pre-sort which index you talk to. So rather than, you hitting my backend and my backend just poof going to your index, it will first go to a model which will say, hey, which index actually should this query go to? And this AI agent will sort your queries into, the corresponding indices live. And that's like, yeah, a cool way which AI will be further integrated into the system. And I think that will more or less address the problem of like optimality.
Okay.
Yeah.
And can you kind of quantify the improvement that you get using your system plus going to one of those models directly and just asking the same question?
Oof, yeah. So this also totally depends on the domain. But for instance, if the model never saw the information before, then of course it will never be able to present a coherent response. And these models do hallucinate. They do tend to hallucinate, and that's why you want to be extra sure that it actually has the knowledge and context that it needs in the back end to be able to answer those questions, right? And I think Vito will address this question more in his talk about like how much, to what extent RAG improves the system, but quite a bit, I would say. Yeah. Yeah.
Just regarding the index is totally independent from the model. So the model is pre-trained, finished, and then you add information as context from the index.
Totally. Yeah. Yep.
How do you write the automated tests for such a thing?
Debugging is a whole nother topic actually in AI, because this is like I said, evaluation is a really it's a really difficult problem, right? So automated tests for just the standard backend API calls and stuff like this is just done with standard like CI/CD stuff. But if you're talking about the actual responses from the models, let me come back to you in a year. And yeah, yeah, yep.
There's one question: multiple algorithms are involved, but how do you estimate? Probably it depends also on the overall solution. What's the time complexity or space complexity, roughly speaking?
The whole solution. That's a good question. So we have this. I would say, ideally the AI is choosing the algorithm in the back, depending on how much data there is. So you could actually like fix a time budget and say, okay, you're never going over 2 seconds or whatever. But with our current system, it's like, let's say we have linear scaling with the amount of data that you put in, but the slope is very low. So that's the good thing. Yeah.
Sorry to interrupt, but we need to continue, or the pizza will be very cold.